This lesson will be about absolute convergence, the ratio test for absolute convergence, and the root test for absolute convergence. So previously we've studied alternating series, so a series whose sign alternates back and forth. And now what we're going to do is take that and say, well, some alternating series, even when you take the absolute value of each of their terms, so now we make them all positive and add them up, some of those converge and are sometimes actually easier to work with than the alternating series itself. And if you take the absolute value of all the terms and add all those up, and that thing converges, you would say that the statement absolutely converges. So first thing I'm going to do is define absolute convergence. And something would absolutely converge if you had this as your series, the infinite sum of the sequence A sub n. We would say that this absolutely converges if this was convergent. And so basically it's like, as I said a minute ago, if you want to know if this thing absolutely converges, then you take the absolute value of all the terms, or whatever A sub n is, and if you can show that that's convergent, then you would say that the series is absolutely convergent. And then we're going to do two tests, both of which, the ratio test and the root test, both of them will test for absolute convergence, and then that'll be that. So first example. Is that series, and the first term would be, just to give you a few terms, the first term is 1 and minus 1 over 2 squared, then plus 1 over 3 squared, etc. So it alternates back and forth, and the denominator is 1 squared, 2 squared, 3 squared. So anyway, that's the original series we're dealing with. If you take the absolute value of this to test for absolute convergence, we take the absolute value of that term, and the absolute value would be, well, negative 1 to the n minus 1, regardless, is going to become 1. And then you're left with n squared. And now you have to think, does that sum converge? And of course it does. And hopefully, if you hit pause and stare at it and think about why, now you've resumed, and you hopefully have had the thought that it was a p-series with the power greater than 1, so it's convergent. Thus, if this is convergent, the absolute value of that was convergent, then this itself, we would say it absolutely converges, or that it's absolutely convergent. Okay, I'll do another one here. This one we've actually seen before. Negative 1 to the n minus 1 over n. This thing is actually the alternating harmonic series, right? If you looked at this as just 1 over n, it'd be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. But this will cause the signs to alternate. I'm not going to write the terms out like I did here, but it's the alternating harmonic series. If you remember, the harmonic series itself was, well, we'll get there in a second. So let's take the absolute value. No need to spoil the end of this story. Absolute value of the whole thing here. And I didn't write that step, this step right here. I just mentally took the absolute value. But why not? So n equals 1 to infinity, negative 1 over n. That'll become 1 over n or 1 over n would stay as 1 over n. And this thing is divergent. It's divergent because of the fact that the harmonic series is divergent. And we already had discovered that the alternating harmonic series from our lesson on alternating series, the alternating harmonic series was actually determined to be convergent. And if you're wondering why did I say divergent, well, I said that the harmonic series was divergent. The alternating harmonic series is convergent. But the point for the purposes of this lesson are if the alternating series, excuse me, the alternating series converges, the absolute value of the series diverges, then we call this thing conditionally convergent. By this thing, I mean this one. That is called conditionally convergent. In other words, we couldn't say that it's absolutely convergent. Under one condition, if it's alternating, it converges. Under another condition, the absolute value of it diverges. So that's called conditional convergence. And one point about absolute convergence, which I haven't fully shown here, but it's pretty simple to imagine. A theorem says absolute convergence implies convergence. And if you think, well, so what? Like, if I already know that thing's convergent, why would I prove it to be absolute convergence? I'd ask you to turn that statement around and think rather, if you had some series that was slightly annoying to deal with because of its alternating nature, then you could determine if it absolutely converges, and then if you know that, well then you know it converges. Without having to directly show that it converges, you could just show that the absolute value of that series is convergent. So, and I think this would make sense to most people why absolute convergence implies convergence. And if you think about, just picture a series that is alternating, and if you're not sure whether or not it converges, make all of it positive. And then if all of it being positive converges, then clearly the positives and negatives would work themselves out to converge as well. Okay, so let's see an example of using this. That says cosine n over n squared, which will be cos 1 over 1 squared plus cos 2 over 2 squared, etc. Well, let me just write out another one. Cos 3 over 3 squared. And you might think to yourself, well, that's really not a big problem. Or at least you don't see where the alternating part comes from. But think about the fact that, first of all, radians, get your head in radian mode. Cosine of 1 is going to be positive. If you're thinking, what the heck does that mean, cosine of 1? Remember, if you start at 0 degrees and you go up 1 radian, well, this would be 3.14 radians going over to 180 degrees, sorry. So 1 radian would be up here in the first quadrant. So cosine is going to be positive there. 1 squared is obviously positive. That term, though, would be negative. Cosine of 2 is roughly 2/3 of the way over to 190 degrees, which is going to be in the third quadrant, which will make it negative. Also, cosine of 3 will be negative. And then if you do cosine of 4, thinking about cosine of 4, that's going to be past 180, but it's going to be in the third quadrant now, which means that term is going to be negative. So we have a positive term, a negative one, another negative one. The one after that will be positive. So you've got to deal with the fact that you're working your way around this unit circle over and over and over again, and it's relatively annoying to have to deal with that. So something you can do is you can take the absolute value of the original series. So this is the point that I was making over here when I said sometimes you don't want to test for convergence, you'd rather test for absolute convergence. Well, the absolute value of cosine of n over n squared, now we can compare it, right? We've done comparison tests before. That's going to be less than 1 over n squared. Because cosine of n, the absolute value of cosine of n is always less than 1. And if you're wondering why we couldn't have just said that from here, it's not unfair to say that each of those terms is less, but if we're going to do a comparison test, we need to make sure, remember that everything had to be positive and all that sort of stuff. So just making sure that it's all positive so that we satisfied all of our initial conditions for our different theorems. Now we have the infinite sum of 1 over n squared, which of course is a p-series again. This is a p-series and it is convergent. So if that is less than that, then that is convergent. If this is convergent, then this absolutely converges, in which case absolute convergence implies convergence. So we would say this thing now absolutely converges, or we could just say it converges, right? Okay, onward we go. So I'd say now we've kind of checked off like defining absolute convergence. Now we're going to move to the ratio test, and I don't want to call it the ratio test just because I think you'll get caught up in everything's just a test for convergence, but the ratio test and the root test are tests for absolute convergence. So when you remember a ratio test, remember ratio test for absolute convergence instead. So the ratio test for absolute convergence, there are 3 different cases that can happen in the ratio test. Let me get rid of this. The first case, well, first of all, the ratio that you're taking is you're basically studying the ratio of the next term to the current term, which we would name a sub n plus 1 over a sub n. So case number 1 is, first of all, we're going to consider a sub n plus 1 divided by a sub n. So we're going to take the next term in the sequence and divide it by the previous term in the sequence. And what we're effectively doing is kind of setting up a comparison to a geometric series. So think about geometric series. You can multiply by 2/3 to get the next term, multiply by 2/3 to get the next term. If you did multiply by 2/3, you have a convergent geometric series because the common ratio is absolute value is less than 1. So we're going to look at the ratio from the next term to the term you're on. We're going to take the absolute value of it so that we don't have to worry about the sign. And then we're going to let n go to infinity. So as you get very, very far out in your sequence, we're saying, what does the ratio tend to? If you were to phrase it as a common ratio, what does it tend to? If this tends to some number that's less than 1, then that implies absolute convergence. So like I said, it's a test for absolute convergence. Case number 2, and this should make sense because if the ratio is less than 1, then it's behaving like a geometric series that converges, thus this series would converge, thus it's absolutely convergent. Case number 2, same exact thing. But in this case, it'll be greater than 1. So if the ratio is greater than 1, then the terms are exploding, in which case, divergent. And case number 3, same exact calculation again. If it equals 1, then that means every term way out in this sequence, each term basically looks just like the one before it, in which case we're going to say that this thing is inconclusive. And if you're wondering, like, well, why is that the case? Well, there's something sort of funny that happens, and I can show you this in 2 different ways. The first way is the infinite sum of 1 over n squared. If you were to take the a sub n plus 1, okay, a sub n plus 1 in this case, so let's study the limit as n approaches infinity of a sub n plus 1, that'll be 1 over n plus 1 squared over, we're doing a sub n plus 1 over a sub n, 1 over n squared. And that will be equal to n squared over n plus 1. So limit as n approaches infinity, n squared over n plus 1 squared. And if you were to FOIL this out and then study the fact that the numerator and denominator are codominant, you would say, you'd see that this limit equals 1. And side note, this guy is convergent. And I know this thing is convergent because it's a p-series. Okay? Now, if you're just to bring us back, I'm trying to explain to you why, if the ratio equals 1, we're inconclusive. So the other one I would pose to you is our friend, the harmonic series. So we're just going to take the limit of the next term, which will be 1 over n plus 1 over 1 over n, which will be limit n over n plus 1, and same deal here. That limit approaches 1. If that limit approaches 1 and that limit approaches 1, and we know this thing is divergent because it's harmonic, then obviously if it equals 1, we can't make any good conclusion. So if the ratio tends to be less than 1, absolutely convergent, just like in a geometric series. If it tends to be greater than 1, divergent, just like a geometric series. If it equals 1, though, and this part, like I said, is a little more nuanced than the geometric series argument, is that we're inconclusive. We could be a convergent, could be divergent, in which case you need to maybe pursue a different test. Okay, so let's do an example. Just going to do a quick time check. Okay. So an example is the following infinite series. Okay, so -1 to the n, n cubed, over 3 to the n. So the first thing we're going to do is take the limit as n approaches infinity of a sub n plus 1, and I'm going to make sure I don't make any mistakes with these writing them out. N plus 1. Okay, that's a sub n plus 1. That's a sub n. And when you simplify this, I'll leave it to you to do the algebra, but you end up with limit as n approaches infinity of 1/3 times n plus 1 over n cubed, and now that thing goes to 1/3, and which means as you get really far out in the sequence defined by a sub n here, as you get really far out, the next term is 1/3 of the term you were just on, in which case we would say that this thing is absolutely convergent. Okay, I'm getting rid of our test here so that I can do another example. And this one actually lands in an interesting spot, n to the n over n factorial. So again, we're going to do a sub n plus 1, the limit as n approaches infinity of a sub n plus 1, which will be, this one's sort of super annoying to write out actually, n plus 1 to the n plus 1 over n plus 1 factorial, all that over n to the n factorial. Now again, I'm not going to do all the algebra, but if you just manipulate, and you're going to have to really probably recall some of your factorial skills on this, you eventually get to this, which is this. I'm leaving off my limits, sorry, I'll write my limits sort of scratchy there. Now if you divide each inside, you can turn this into limit as n approaches infinity of 1 plus 1 over n raised to the n. That thing actually goes to e. And just a side note here is we're going to talk a lot more about e soon. And if this statement doesn't make a lot of sense to you, all I would ask you to do is put a really big number in for n. Do like 1 plus 1 over 100, raise it to the 100. Do 1 plus 1 over a million, raise it to the million, and you see you get really, really close to e. We'll talk more about that soon. But if that goes to e, and remember e is 2.7-ish, then that thing is going to be greater than 1, in which case this guy is divergent. That would be per the second condition of the ratio test. And like I said, the basic deal with the ratio test is it's creating a it's taking the series and viewing it through the lens of a geometric series. Okay, last thing is a root test. The root test is going to be very similar. First case, we're going to compare the limit as n approaches, case number 1, limit as n approaches infinity of the nth root of the absolute value of the sequence. Okay, if that's less than 1, then absolute convergence. If all that stuff is greater than 1, it's divergent. And if all that stuff equals 1, it's again inconclusive. And I'll give you an example of this, and then we'll be finished. This is 2n plus 3 over 3n plus 2, all raised to the n. You can see the ratio test would be pretty useful for factorials. The root test will be much more useful when we have the variable n in the exponent. So if we take the limit as n approaches infinity of the nth root of that, of all that, then we end up with just the fraction 2n plus 3 over 3n plus 2, because the nth root of the nth power. Now that limit is 2/3, and if that limit is 2/3, then we've satisfied the condition for absolute convergence. So brief discussion here, conclusion. We talked about absolute convergence in the context of whether an alternating series is convergent itself, but its absolute value was not convergent. We used the harmonic series to show us that the alternating harmonic series would be conditionally convergent, whereas a series whose absolute value converges as well is absolutely convergent. So we talked about conditional versus absolute convergence. Then we had a ratio test for absolute convergence, and I should add root test for absolute convergence, as I asked you to remember. I'm not just going to call it the ratio test and the root test, because we might think that they prove convergence, which they do implicitly, but it is good to know that they prove absolute convergence. So we proved absolute convergence via ratio test and via root test.